Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 16 on complex analysis and today's topic of discussion is Cauchy's integral theorem. Students, first let me read the statement. According to this theorem, if a function f of z is analytic and its derivative f prime z is continuous at all points inside and on a simple closed curve C, then integration along closed curve C f of z dz is always 0. Now let us understand what is the actual meaning of this theorem. Suppose we have a closed curve C and we have a function f of z which is analytic at all points inside and on the closed curve C. By analytic, I mean to say that this function f of z is continuous and differentiable, or this function f of z satisfies the CR equations at all points inside and on the closed curve C. Apart from that, the derivative of the function, that means f prime z, is continuous at all points inside and on the closed curve C. If these two conditions are satisfied, then according to Cauchy's integral theorem, integration along closed curve C f of z dz is always 0. Now let us derive this part. So integration along closed curve C f of z into dz is equal to integration along closed curve C. We know according to the basic representation of function of a complex variable is given by f of z equal to u plus iota v and dz equal to dx plus iota dy. Now let us substitute the values of f of z and dz here. So f of z equal to u plus iota v and dz is equal to dx plus iota dy. Now let us simplify this part. Integration along closed curve C u dx plus iota into u dy plus iota v dx minus v dy. Now let us separate the real and imaginary parts. So integration along closed curve C f of z dz is equal to integration along closed curve C u dx minus v dy plus iota integration along closed curve C v dx plus u dy. Next, let us apply the Green's theorem, and according to this Green theorem, integration along curve C m dx plus n dy is equal to surface integration of del n by del x minus del m by del y into dx dy. For this integral, m equal to u and n equal to minus v. So after applying Green's theorem for this integral, we will get surface integration of minus del v by del x minus del u by del y into dx into dy plus iota. Again let us apply Green's theorem for this integral. So for this integral, m equal to v and n equal to u. So we will get surface integration of del u by del x minus del v by del y into dx dy. Now let us apply Cauchy-Riemann equations, and according to Cauchy-Riemann equations, del u by del x equal to del v by del y and del u by del y is equal to minus del v by del x. So this term minus del v by del x can be written as del u by del y. So we can write surface integration of del u by del y minus del u by del y into dx dy plus iota surface integration of, again, del u by del x is equal to del v by del y. So replacing del u by del x by del v by del y. So del v by del y minus del v by del y into dx dy. Del u by del y minus del u by del y, 0, 0 into something 0. So ultimately we will get 0 plus iota into 0. So the value of this integration along closed curve C f of z dz will be equal to 0, hence proved. Now let us learn another theorem, which is extension of Cauchy's theorem to multiple connected region. Students, first let me read the statement. According to this theorem, if f of z is analytic in the region capital R between two closed curves C1 and C2, then integration along curve C1 f of z dz is equal to integration along curve C2 f of z dz. Now let us understand the meaning of this theorem. So according to this theorem, we have a function f of z which is analytic. That means this function is continuous and differentiable in the region between two closed curves C1 and C2. That means in this region, the given function f of z is analytic. If this is true, then according to this theorem, integration along curve C1 f of z dz is equal to integration along curve C2 f of z dz. So this is the statement of this theorem, and please try to derive this theorem by yourself. Next, let us apply this theorem to this type of region. So we can write integration along curve C1 f of z dz is equal to integration along curve C2 f of z dz plus integration along curve C3 f of z dz plus integration along curve C4 f of z dz plus integration along curve C5 f of z dz. Okay? Now let me solve two numerical problems. Problem number 1. Find the value of this integral where C is the circle modulus of z equal to half. Students, before solving this problem, I want to explain a very important concept, which is singular point or pole. Singular point basically means it is the point at which a function f of z is not analytic. That means at that point our given function f of z does not satisfy the CR equations. Example, suppose we have a function f of z which is equal to z square divided by z minus 1. So for this case, when we put z equal to 1, this function becomes infinite. So therefore z equal to 1 is said to be the singular point for this function f of z. In other words, we can also say that this z equal to 1 is a pole of order 1. Second example, suppose we have another function f of z which is equal to z square divided by z to the power 4 minus 1. So for this case, z equal to 1 is said to be the pole of order 4. A dedicated lecture on singular point will be uploaded in near future. Now let us solve this problem. So according to this problem, f of z equal to this one. So given f of z is equal to 3 z square plus 7 z plus 1 divided by z plus 1. So here we have seen that z equal to minus 1 is the singular point for this function f of z. Here z equal to -1 is the singular point, is the singular point for the function f of z. Again, we have seen that the given circle whose radius half and center at origin does not enclose any singular point. In other words, we can say that this function f of z is analytic at all points inside and on this circle modulus of z equal to half. So, therefore, by Cauchy's integral theorem, the value of this integral is 0. Okay? So, let me write these points. Since the given circle modulus of z is equal to half with center at z equal to 0 and radius equal to half does not enclose any singular point. So, by Cauchy's integral theorem, we have integration along curve C 3z square plus 7z plus 1 divided by z plus 1 into dz is 0. Answer. Next, let me solve this second problem, and according to this problem we have to find out the value of this integral where C is the circle modulus of z plus 1 equal to 1. So, according to this problem f of z equal to this one. So, given f of z is equal to z plus 4 divided by z square plus twice z plus 5. Now, let us find out the singular points. The singular points or poles can be obtained by putting denominator equal to 0, by putting denominator equal to 0. That is z square plus twice z plus 5 equal to 0. So, therefore, z will be equal to minus b minus 2 plus minus b square 4 minus 4ac minus 20 by twice a 2. So, z will be equal to minus 1 plus minus twice iota. So, the singular points or poles are z equal to -1 plus twice iota and z equal to -1 minus twice iota. These singular points will be located at these points on the eigenplane. So, this is the location of this singular point and this is the location of this singular point. Now, let us draw the given circle whose radius is 1 and center is at -1. After drawing this circle, we have seen that there is no singular point inside or on the given circle. In other words, we can say that this function f of z is analytic at all points inside and on the given circle modulus of z plus 1 equal to 1. So, therefore, by Cauchy's integral theorem, the value of this integral is 0. Now, let me write these points. Since the given circle modulus of z plus 1 equal to 1 with center at z equal to -1 and radius 1 does not enclose any singular point So, by Cauchy's integral theorem, we have integration along curve C z plus 4 divided by z square plus twice z plus 5 dz is equal to 0, which is the answer. So, this is all about today's video and I hope that you have learned a lot from this video.